Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel. Today's topic of discussion is proportional valves. Our objective is to examine how proportional valves influence both actuation speed and direction in a hydraulic system. As you're no doubt aware, certain properties influence the observed behavior of a hydraulic system. Pressure influences actuation strength, flow rate influences actuation speed, and valve position influences actuation direction. With some understandable overlap and interplay, control of these properties are customarily the responsibility of different components within a larger system. Pressure relief valves limit system maximum pressure. Flow control valves limit flow, and directional control valves stop, start, and change flow direction. A proportional valve, in contrast, is a device that does two things at once. Proportional valves control flow as well as stop, start, and change flow direction. Proportional valves are in effect combined flow control valves and directional control valves. Total flow rate available to a system is a function of pump output. Flow control valves are narrow restrictions that throttle flow rate down to the desired value, with the surplus pump output being spilled over the pressure relief valve. While inexpensive, there is a bit of drawback to this method because every time a system needs to vary flow rate, the flow control valve needs to be manually adjusted, or multiple flow control valves with multiple switched routes need to be added to this system. Additionally, a directional control valve still needs to be employed with this system. The directional control valve, being solely an on or off switching device, can induce pressure shocks as passages are selectively fully opened or fully closed. Proportional valves, in contrast to a regular solenoid-operated directional control valve, are electrically actuated valves that make use of an analog rather than a digital input signal. Analog means continuously variant within a given range. Digital or discrete, in contrast, means fully off or fully on with no intermediary value. A traditional solenoid-actuated directional control valve is digital in nature. For example, consider a two-position, solenoid-actuated directional control valve rated for 24-volt DC. When 0 volts is applied, the valve is fully spring offset into the deactivated closed position. When full 24 volts DC is applied, the valve is fully shifted into the activated open position. Acceptable low and high inputs for digital systems do have upper and lower tolerances. However, intermediary values between these tolerances are invalid and can lead to undesirable operation of the valve. Analog signals, in contrast, can take intermediary values in that the full range of 0 to 24 volts is now an acceptable value. An input of 0 volts still fully spring offsets the valve into the deactivated closed position, and an input of 24 volt DC still fully shifts the valve into the activated open position. However, assuming linearity, an input of 12 volts effectively half shifts the valve into the activated position, an input of 6 volt quarter shifts it, 18 volts 3/4 shifts it, and so on. These intermediary positions assumed by the infinitely variable valve, rather than inducing undesirable behavior as previously, allow different levels of flow. Again, assuming linearity, fully shifted means full flow. Half shifted means half flow. Quarter shifted means quarter flow, and so on. By the way, I'm making some obvious simplifications here. In addition to varying the level of the analog signal, polarity can also be changed, as we'll learn in a moment. While substantially more expensive than a regular flow control valve and directional control valve combination, a proportional valve offers additional functionality in a single package. In addition to simultaneously controlling actuator speed and direction, being analog in nature, the pressure shock associated with a traditional fully closed or fully open directional control valve can be mitigated in that applied voltage can be smoothly ramped up over time, thereby slowly opening the valve and suppressing the shock. This ramping event controls the acceleration and deceleration of the applied load, as we'll learn in a moment. Additionally, proportional valves sometimes include sophisticated feedback mechanisms that allow them to not only receive an input signal, but also send an output signal that can be monitored by a control system to perform incredibly stable, precise, accurate, and repeatable movements of an actuator despite a changing external environment. Not sure if you can tell or not, But I'm getting kind of excited here because proportional valves blow wide open the doors of many advanced topics, including open and closed loop control, PID control, and more. I'll do my best to curb my enthusiasm for the time being and keep this lecture inside the confines of a general introduction to proportional valves. This being said, let it be known proportional valves are extremely sophisticated tools which I delight in using when discussing these more advanced topics. There are several different variations of proportional valve construction, most of which employ valve spools with V or U-shaped control edges that open up very gradually, allowing accurate control of the flow rate as spool position is infinitely varied. Consider a 3-position proportional valve making use of a spool positioning apparatus known as a linear force motor. You note the main valve schematic symbol includes a spring-centered closed position, a straight-through position, and a cross-connect position. The schematic symbol for the linear force motor kind of looks like a single solenoid with a variable slanting arrow. A linear force motor is a sophisticated valve positioning mechanism that moves the spool with respect to the applied voltage magnitude and polarity. Long story short, polarity determines the direction of spool movement, and magnitude determines the distance. The application of positive voltage moves the spool into the straight-through P to A position, and the application of negative voltage moves the spool into the cross-connect P to B position. In ideal, perfectly linear and predictable circumstances, assuming a range of positive to negative 10 volts, the application of 0 volts perfectly spring centers the spool into the closed position. Full positive 10 volts results in a full flow in the straight-through P to A condition, and full negative 10 volts results in full flow in the cross-connect P to B position. Intermediate positive and negative voltages result in perfectly proportional, hence the name, intermediate flows. We'll come back to discuss non-linearities like deadband and hysteresis in a moment. This being said, this ideal graph isn't really that far from the truth. Alternatively, proportional valves can be constructed using 2 proportional or variable solenoids. You'll note the schematic symbol for these style proportional valves show 2 solenoids with slanting variable arrows. Finally, a proportional valve can also be constructed using a piggyback style valve, where rather than an electrically actuated linear force motor or proportional solenoids directly acting upon the primary spool, an electrically actuated pilot spool indirectly shifts the primary spool via pilot pressure. These multi-stage, piggyback-style proportional valves are employed in high-pressure, high-flow rate applications. You'll note piggyback-style proportional valves include the pilot pressure stage in their schematic symbol. Alternatively, a piggyback-style proportional valve can also be drawn schematically as a small, electrically actuated valve proportionally actuating the pilot line of a larger pilot-actuated primary valve. Thus far, a proportional valve is almost exactly like a solenoid-actuated directional control valve with 2 major exceptions. One being that the spool position is infinitely variable via continuously varying analog input signal, and 2 being that the spool includes V-shaped grooves, allowing variable flow rate as a function of position. Finally, because I guess this is an identifying characteristic too, ordinarily polarity of the applied voltage determines the direction of spool movement, and magnitude determines the distance of spool movement. Long story short, a proportional valve is a directional control valve that controls flow rate. Or is it a flow control valve that controls direction? The world may never know. Regardless, proportional valves perform both tasks. But wait, that's not all. As previously mentioned, proportional valves often include spool position feedback mechanisms. Ordinarily, this comes in the form of an LVDT, or a linear variable differential transformer. Not sure if I've got enough time to go into detail how an LVDT works, but in summary, it produces an output voltage proportional to spool position. Again, assuming a positive 10 to negative 10 volt range, 0 volt feedback means that the spool is perfectly centered. Positive 10 volt feedback means it's fully straight through. Negative 10 volt means it's fully cross-connected. And intermediate positions result in intermediate directly proportionate feedback values. We'll examine how this feedback about spool position can be used to our advantage in a moment. Note that not all proportional valves include positional feedback mechanisms like LVDTs, especially for low-cost applications that do not necessitate precision. As previously mentioned, in ideal, perfectly linear, and predictable circumstances, assuming a range of positive to negative 10 volts, the application of 0 volts perfectly spring centers the spool. Positive 10 volts results in full flow in the straight-through P to A direction, and negative 10 volts results in full flow in the cross-connect P to B direction, with the intermediate positive and negative voltages resulting in perfectly proportional intermediate flows. An ideal graph of flow rate as a function of applied voltage might look something like this. Real proportional valves exhibit slightly different behavior. The first peculiarity being something known as dead bands. A more accurate graph of flow rate as a function of applied voltage might look something like this. Dead band is a region of zero flow despite increasing magnitudes of positive or negative voltage being applied to the valve. Deadband is a byproduct of several non-negotiable realities. One being spool overlap, where overlap means the spool land must be slightly wider than the passage it is intended to block to ensure positive seal. Another reality being friction of the spool against the valve body and oil impurities, and another being magnetic effects we'll examine in a moment. The flat zone characterizing the deadband means a certain minimum amount of voltage must be applied to the proportional valve for it to open at all. This is a perfect point in this lecture to answer a question that is undoubtedly burning in the back of some of your minds. This question being, what is the difference between a proportional valve and a servo valve? My response is quite simple. What's the difference between a super expensive sports car and a super expensive sports car? A proportional valve is any continuously variable, electrically modulated directional control valve with more than 3% center overlap, whereas a servo valve is any continuously variable, electrically modulated directional control valve with less than 3% center overlap. Given proportional valves are already known to have tight performance standards, this is to suggest that a servo valve is a proportional valve with even tighter performance standards. For this reason, I do not differentiate between proportional valves and servo valves because a Venn diagram of the two would include servo valves as a subset of proportional valves. As we discussed, a certain amount of overlap is necessary to ensure positive seal and zero flow in the closed center position. However, the spool and passages can be machined to such tight tolerances that this overlap is minimal. You've got yourself a servo valve. This is often called a line-to-line spool rather than overlapped one. This is to suggest that a servo valve may exhibit less deadband and more linearity of flow rate as a function of applied voltage than a similarly rated proportional valve. To be honest, I find this semantic distinction annoying, excessively trivial, and unworthy of consideration, which might dismay those of you that just love servo valves. We get it. Servo valves are special. But when you get right down to it, a servo valve is a proportional valve, and you're going to have to get used to it. By the way, you may see charts of flow rate as a function of applied voltage in manufacturer datasheets, defining the P to B cross-connect flow as negative since it's going the opposite direction. Be aware of this perspective flip-flop. Other than that, these two graphs are equivalent to each other. Another proportional valve peculiarity is something known as hysteresis, where hysteresis is the spool's tendency to move a predictable amount for increasing voltage magnitude, however, exhibit different amounts of movement for decreasing voltage magnitude. I like to think of hysteresis as the magnetic equivalent to friction observable as slight spool misalignment for equal applied voltages. An analogy might be placing your foot exactly in the center of a tread going up the stairs, but slightly off-center of the tread when you go down the stairs. You're still going up or down the stairs, but you're ever so slightly off position pending direction of movement. Hysteresis is kind of confusing. It's probably best illustrated with an example. Consider a proportional valve with the following applied voltages and the following observed flow rates. In this case, we're ramping up voltage from 0 to positive 10 volts. Note as voltage increases, flow rate in the straight-through P to A direction increases linearly as we'd expect. When plotted, it should look like the highlighted curve. No surprise there.